welcome to our special bonus talk at the beginning of the afternoon session. So Joe Stringer from the VMware Open vSwitch team is going to talk to us about how OVS keeps the kernel flows fresh. And that's something that Joe's been working on for about the last 6 months, and it's surprisingly key to Open vSwitch performance. So take it away, Joe.
All right, thanks. Cool. So a little bit of kind of preparation sort of. This was a dev talk. It was kind of targeted at one of the little rooms over there. So I've got a much bigger audience than I expected, but that's good. I hope you're all interested in this. What I'm going to talk about is a little bit about the threading model that OVS uses to install flows and to delete flows from the kernel. I'll talk about the life cycle of that Datapath flow. Throughout this talk, I'll refer to OpenFlow rules as rules, and I'll talk about Datapath flows as flows. These are separate concepts. This is just the terminology I'm going to use. I'm not going to explain it. I hope that some of you already have some knowledge about this. And I'll talk a bit about some optimizations and some insights that I've had from working in this area for the last 6 months or so. So a recap of the Open vSwitch architecture. The upper half here is the user space, OVS vSwitchD. It has connections to OVSDB and OpenFlow, which is managed in this layer up here. Talks down to network devices into the kernel here. And then this is the way that we actually manage flows. This is, in particular, of proto DPIF. So when an OpenFlow controller installs a rule, it gets installed into this OF proto DPIF. And what I'm going to talk about is how we push that down to the Datapath. So if you zoom in again, so this is all OF proto in the middle here. Main thread, OVS vSwitchD, so OpenFlow and OVSDB is up here. So you can sort of think of this classifier in here which stores the state about the current set of OpenFlow rules and the current OVSDB configuration for how the switch is going to behave. And we have two pools of, and that's managed by the main thread. So the main thread will terminate those connections up there, and they'll place the information into this classifier. So we have handler threads, we have Revalidator threads. A handler thread's job is to take the first packet, classify it, figure out which OpenFlow rules that particular packet applies to, and then push down a flow cache entry into the Datapath, which will then be used for future packets in the same flow. And that allows the kind of performance that we've been seeing in the past day or so. On the other side, we have Revalidator threads. They constantly dump flows from the kernel. They check, is this flow correct? Is this flow idle? And they will delete those flows from the kernel. So it's managing what stays in the kernel. So to go into slightly more detail, the mishandling handler threads install and forget. The first packet goes up to user space. A handler thread will take that packet, classify it, install a flow into the kernel so that subsequent packets can go through a fast path. Once it's installed, how do we delete that flow? How do we know that that flow is still valid when someone installs new OpenFlow rules, when someone reconfigures the OVSDB? Some rules can cause flow table updates as well, which can change that state again. And there's also the statistics that we have to gather from those flows. So this is all cache validation, or what we call revalidation, because this Revalidator is taking flows and it's just constantly validating that they're correct. So the process is we fetch flows from the Datapath. We translate from that Datapath flow format into a user space flow format and run it through a classifier. This allows us to attribute statistics to different rules, different interfaces, things like NetFlow. There are other areas as well. And we can also, this is how we implement L2 learning, things like rule learning. And lastly, we need to check that the flow is correct. I haven't explained, but, so because a handler just installs a flow and then forgets about it, when there is a change at a higher layer, OpenFlow, OVSDB, there's no other mechanism that propagates that change down to the data path. So it's the Revalidator's job to run through these flows and check that if something's changed at an OpenFlow layer, is the data path flow cache still correct? A little bit more zooming details. We use a mark sweep algorithm for this. So we dump flows from the data path. We build up a cache in user space that maps a particular data path flow to a set of statistics that's most recently been seen. Then we sweep and, the other thing is that shows that allows the Revalidator to see what flows are actually in the data path. It checks that the flows are valid and marks a bit in this Yuki entry. The sweep phase iterates through that cache, deletes the old Yuki entries, and if a flow hasn't been seen in a while, so for instance, if a user deletes a flow using OVSDB kettle, something like this, then we'll also attempt to fetch those flows, gather the final statistics, and check that they're correct. The last phase is that we synchronize all Revalidator threads. So we have multiple threads that are going through these phases. Multiple threads dump flows from the kernel, check them, and delete flows, and then they all synchronize together again. Sort of zoom through that, so if I sort of wanted to give a bit of a pause, say, all right, so this is sort of the model that we work with. There are different areas that I have more detail on, and like I said, this is a dev talk, so I'm going to elaborate on different areas, but sort of wanted to check that everyone's still with me. If you have any questions, then it's not a bad time to check.
Hi, my name is Vinay. I'm with eBay PayPal. One of the questions I had was, Revalidator thread is collecting all this, dumping all this flows from kernel, right? And it's also getting attributes and stats.
Yeah.
Is it possible for us to get those stats on a per flow basis so that we can monitor at the user level by writing our own scripts?
So you're talking about gathering statistics from a data path, from the data path flows?
Yeah, because you're already getting that. So
yeah.
Are you stashing it away someplace that we can access? And the reason I'm talking about that is, like, I would like to get a full level stats across my entire cloud.
Yeah, so those stats are cached for the reason that, sorry, I have a little bit of detail to explain, but when a flow cache entry in the kernel's installed, it will accumulate packets. And if we revalidate multiple times, then we need to be able to figure out which stats we've attributed already. And part of the Revalidator is we push the statistics up to the OpenFlow layer. So that allows you to fetch it from the OpenFlow layer. Now, if you did want to build an independent way of checking these stats, you can use something like dbcatl as well. Does that answer your question?
I think actually, Chad, yesterday, I think you were saying that you have, I think was it the Pavlov's that maintains some of that information that will go through and collect stats like the number of flow entries and the hit and miss count? Okay, so the feedback was that was on the bridge or the switch level, but not on the individual flow. Right. So the comment was that some of those statistics aren't available through OpenFlow, like the miscounts. But I think that's I believe that the tool that Rackspace wrote is running OVS dpkettle to get all of that information, and then they're putting it someplace and keeping track of it and graphing it.
My name is Milton Zhu. I'm from Cisco Systems, and I have a question regarding the latency. For the first flow which you established and the subsequent packets, that's assuming like it's a 64 bytes packet and at a 10 gig line rate. So how many packets you will see, how many more packets you see before the kernel flow is established?
So I think the question was if because the first packet misses to the in the kernel and gets sent up to user space,
right,
how long does it usually take before the packet? Yep. So what will happen is that there's a queue that that packets that are missing in the kernel, they get queued up to be sent up to user space. In our experience, usually, most connections start slowly, so they might send the TCP SYN and then the SYN ACK, and they don't usually just start blasting traffic. But if someone did just start blasting traffic, it would fill up on the queue. Eventually, the queue would fill up, and then they would fall off the bottom. And that's this lost count that is shown if you run dpkettle show.
I'm Sumo Wang from HP company. I want to ask you, if the flow is aging, how do you adjust the memory in the kernel on the flow cache? So do you have some algorithm to optimize the some holes left when the flow aging?
So, I mean, this is really focused about the user space side of tell the kernel to install flows, tell the kernel to delete flows. In terms of memory management, that would all be handled by the kernel. So probably not the right person to ask for that, but yeah. I will talk a bit more about things like how we delete idle flows and that sort of thing in my talk. And maybe I should move on. Yeah, okay.
We'll take more questions at the end. Don't worry.
So yeah, that's with this threading model where we have multiple Revalidator threads able to dump these flows, attribute the statistics, and this sort of thing. Basically, it's fast enough. But like we heard in the Rackspace talk yesterday, well, what if we can reduce the amount of CPU that we use? Well, that's more CPU cycles they can sell. So there's always a benefit to trying to improve the performance. So the way that I've been testing this, and sort of disclaimer, this is not a sane way to run OVS, but basically I disabled the megaflow feature, and this allows me to populate the Datapath kernel cache with a large number of entries and test basically worst case. If we had very specific OpenFlow rules, then you would end up filling up the Datapath, and this allows us to push that. So I tend to use TCP CRR. This sets up a connection, basically sets up a very simple connection and sends a byte. Or I'll use nmap and run many nmap processes and scan across a range, and that will cause a lot of flows to be inserted, and that allows me to test how many flows that are supported and how well the algorithms are working for deleting those flows. So flow limits. So how many flows can we support? Okay, well, the way that we work about this is if we want to keep flows fresh for under 1 second, so that means like if something changes in an OpenFlow layer, then we want to say that it's not more than a second before that change gets propagated down to the kernel cache. And this could be defined as whatever you like. This is the value that we use by default. So we set this limit on the number of Datapath flows that can be created. And once we hit that limit, handler threads will stop installing flows in the kernel, and they'll just start processing any upcalls. And I talked about keeping around 1 second, so if it's the last cycle took less than a second, then we can increase the limit of flows that we can use. If it took more than 1,200 milliseconds, then we'll decrease it. If it's 2,000, then we'll decrease it even more. So the only thing is that with this mark and sweep algorithm, well, you can't just mark during the mark phase and then delete during the sweep phase, because the classification of and translation of the Datapath flow into OpenFlow flows and then determining whether that kernel cache entry is correct or not is quite expensive. And we spend the most of our time in the dump flows phase, fetching flows from the kernel and translating them, and then not much in the sweep phase. So if we only delete during the sweep phase, then we end up hitting the flow limit, and then during this entire time here, handler threads would only be executing flows, and they wouldn't be installing new flows. So this causes performance hit. So obviously the solution is to delete flows throughout the dump phase. So another aspect of it is flow dump accuracy. With the kernel interface, there's no guarantee that we will dump an exact copy of what's in the kernel cache. We have multiple threads inserting and deleting flows. We're dumping in batches. The flow dump is basically just an index into a table, and if we insert a new flow, then that index is incorrect. And so this can cause us to either duplicate flows, which is to say that the same kernel cache entry is sent back up to user space twice, or we may miss them because a flow is inserted, a flow is deleted, and then we start dumping from the next batch from later in that flow table. So this is an assumption that we work with. The way we work around that with in the user space is we keep that UKey we create the UKey cache at the start, and then at the start of the dump phase, and then we'll keep that around until the sweep phase. So if different threads end up handling the same flow, then they'll be able to recognize that flow was already handled. So the translation cache is one feature that I worked on recently. It's targeted at basically removing some of the cost of translation and classification. So when we translate and we determine which OpenFlow rules or which interfaces that statistics need to be attributed to, we cache exactly what those pointers are to those rules, so that later on, the second time through, we can just look up this cache and we can attribute statistics directly to that rule rather than doing the entire translation process. Now, this is good because if the flow table never changes, then the first time that a flow is dumped, we build up this cache. The next times, we can always just use this cache, and it's much, much faster. But when the OpenFlow layer changes, then we have no guarantee that this cache is correct anymore, because we don't know that the flow is correct, and the cache is based on the last translation of that flow. So I call this full revalidation. So we have to go back through that whole translation process again. Now, what we do to try to alleviate that is, if we're in a situation where we're pushing the limits of the number of flows that we can support and dump within a reasonable amount of time, then we start deleting low throughput flows. And the reasoning behind this is that if we need to perform full revalidation for every single flow in the data path, that's much more expensive than the simple case where you can just use this cache. So if nothing's changing, then we build up a certain number of flows that we can support, and we're just attributing stats using the using the cache, and we can support that many. As soon as something changes, we have to do full revalidation, which is much more expensive, and now we can't actually meet our 1 second limit on our dump. So that means that we're going to end up deleting those flows anyway, because we end up deleting those flows anyway. So if it's low throughput, then it's likely going to have less impact on that flow's performance if we delete those ones rather than deleting some larger flow or flow that's seeing a lot more traffic. So again, I wasn't sure that I was going to be presenting in this room, so that might be a little bit small, but so we dump the flow, we check that it's idle. If the flow is not being used, then we're going to delete it. There's no use keeping a cache entry around if it's not being used. We create this ukey entry, and we check if there's been any OpenFlow changes. And this is where the optimizations come in. So if the OpenFlow if something's changed at the OpenFlow layer, then we check if we've been seeing a lot of traffic. If we're seeing a lot of traffic, then it's worth performing full revalidation and trying to keep that flow in the kernel so that there's less performance impact on those flows. If it's not seeing much traffic, we'll just delete it as an optimization so we can get back to a stable state sooner. Now, if nothing's changed at the OpenFlow layer, then we'll just use this, we'll build this this translation cache, and we'll attribute the statistics, execute those side effects, and we're done. And this provided about a 50 to 80% performance increase in the Revalidator, so that says that we can support that many more flows in the kernel with these changes. The next feature, which I'm working on right now, it's not quite upstream yet, but I hope to get that in soon, is unique flow identifiers. Now, the motivation behind this is that every time there's a flow operation, this is inserting a flow into the kernel, or deleting a flow from the kernel, or dumping those flows from the kernel, we send the full flow key, which is the original description of the packet when it first came into the data path. In addition, when dumping flows, we dump back the mask and the actions, and this is quite a bit of data, especially when you're talking about dumping around about 100,000 flows every second. The number one result in perf that I saw while doing this testing was trying to get the kernel trying to translate its internal format for the kernel cache back into netlink to send across the socket. So the solution that I've been working on is to replace this with a identifier. When a handler creates a flow cache entry, we send this ID as well as the key, mask, and actions. Now Revalidators can just request only the ID in the stats. So basically the handler creates a cache of the key, mask, and actions that the Revalidator can use later on. This means that we don't have to transfer all of that information down to the kernel, or up from the kernel and back every time that we want to dump flows. And so there's another sort of 50% performance increase for Revalidators there, which gets us to around about the 200,000 number of flows. That's pretty much what I had to discuss. I have a few more slides if people are interested, but it's not a bad time to open up for more questions. If you're interested in the future, I can go first.
I have a couple of questions on testing this thing. I was running some perf tests, and during that process, I figured out that it's very hard to figure out, like, at any point of time, what is the exact time interval the revalidation logic is using. Like, I think it starts off at 10 seconds. It could go to like 1 second, depending on the load and other things. So
here's a slide I prepared earlier.
Okay.
We have this concept of a max idle time for a flow. So I didn't mention it before, but if a flow is not being used, then we won't delete it for about 10 seconds currently on master. Now, if if the number of flows is exceeding our limit that we have in user space right now, then we're going to cut that down and we're going to start to prune flow entries that haven't seen traffic in the last 100 milliseconds. Well, yeah.
So would it be useful to expose some of this information in the OVS dpkutl like show or something? Because we see the number of misses, but we don't see this information. And if we try to use GDB or something to get this information, it affects those timings and they get messed up. Like.
So there's a OVS app-kettle command for this, which I can put on my slides for when we put them up for later. You can refer back to that. It's just OVS app-kettle, you go up call show, and that will show the current number of flows in the Datapath, the current number of U-key entries per Revalidator, so you can see how many flows that each Revalidator is handling. And there's a few other little bits and pieces around this.
Awesome. Okay. And the next question I had was about, so if say a particular flow is getting revalidated too often or it's getting deleted too often in Datapath, is there any way to like correlate it with the corresponding OpenFlow flow in the OFCutl?
So at the moment, we just, we more or less set a flag when something changes at the higher layer, and then we revalidate everything. So a possible future optimization would be to determine which OpenFlow flows map down to which Datapath flows, and only revalidate something that changes based on the OpenFlow change. But I haven't looked into that too much quite yet.
Okay, thank you so much.
Hi, Rich Lane, Big Switch Networks. I have a question. Why don't you modify the kernel flows instead of deleting them when there's a big TCP connection that has actions changed?
I don't have an answer for that straight off the bat. I guess as a sort of evolving from a simplest model possible to something more complex, having one thread installing the flows and a different thread deleting the flows is sort of a consistent model that's quite easy to understand. It's a potential area to look at. I think maybe Jarno has some.
Jarno Rehan from OVS team. So if I understand correctly, you asked whether why don't we update the kernel flow? We do update the kernel flows as much as we can, but that updating takes a lot of time, and we can't update them all in 1 second. So we choose to delete some of the flows instead of updating them. And we choose to delete the flows that haven't seen so much traffic to prioritize the better flows for updates. So.
One other point there, in the sort of history of Open vSwitch, we actually used to do that, if you remember. And one problem, if you're trying to modify the flows in kernel, user space needs to know what flows are there. And there's a massive amount of synchronization cost keeping the user space copy of what's in the kernel data path consistent with what's actually in the kernel data path. And the nice thing about this model is the mishandlers can install stuff in the kernel and don't have to update any internal state or take any locks, and it's completely independent of what the revalidators are doing. So, you you trade consistency for performance in this particular case, but that's sort of where we ended up on that. That's what I was thinking about when we initially designed this, at least. Yeah.
All right, that's all the time we have for questions. Let's thank our speaker.